In this video, we're going to look at one alternate way of setting up proportions for similar triangles. So if we look at exercise 1 here, we have the diagram of triangle ADE, which has a line segment connected from B to C and has been drawn parallel to DE. So we want to justify first why the two triangles shown are similar. So we're looking at the triangle of ABC as well as the triangle of ADE. Now, one thing you might notice automatically is these two triangles share one special angle right here. If they both share that angle A, that's our reflexive property. So we already know that angle A is congruent to angle A because of the reflexive. The other piece of information that's given to us in here is that those parallel lines exist. So we know by now that parallel lines form what's known as congruent corresponding angles. So because of those angle pairs that are in there, we're going to mention that parallel lines form congruent corresponding angles. And that being said, that leaves us with enough information to show the triangles are similar. As long as you can show two congruent angle pairs, in this case we really could have shown all three. We don't need to in a formal proof, but we know those triangles are similar. In part B, we're given that AB has a length of 6 and AD, the entire side, has a length of 10, while BC has a length of 10 and AC has a length of 9. And we're going to set up proportions now to find the values of AE, CE, and DE. Remember, the sides are always in proportion once we know the triangles are similar. So if we start with finding AE, we're looking for the entire piece here, and I'll call it X. One way we can set up this proportion is looking the smaller side of AB is 6 over the larger side of AD being 10, and that's equal to the smaller side of 9 over the entire thing of X. When we cross multiply, we should end up with 6x equal to 90. And when we divide both sides by 6, we end up with x equal to 15. So our first value, or our first side we were looking for, AE, is equal to 15. When I go to try to find the second part, now the second side we're looking for is CE. We notice that that is right here. And we already had the whole length now is 15. We have the top part for the smaller triangle is 9. So when we subtract, we're going to end up with CE equal to 6. One missing piece for us is DE. So I'm going to call it Y just so I have a new letter. If we used X, as long as we're being careful, it's just fine. But I'm going to still use the 6 and the 10 from our original proportion, which is okay. 6 went with the smaller triangle, just like 10 is with the smaller triangle here. And the larger triangle is mapped onto DE, so that's going to be where Y is. We'll end up with 6y, this time equal to 100. But when we divide both sides by 6, we're going to get a long repeating decimal. So I'm just going to put it into a fraction and say it's 50 over 3 when we simplify. So for right now, the length of DE is equal to 50 over 3. Now, there is something unique that stands out about this situation, and we're going to look at the ratios that could be formed in part C. So when I'm here at part C, the first thing I want to do is look at AB and BD. So we know AB was 6, and we can calculate that BD is 4 since the entire length was 10. And it said to simplify, so I'm going to have a ratio of 3 over 2 here. AC was 9, and we calculated CE to be 6, which also simplifies to 3 over 2. And finally, BC had a length of 10, and we found DE to be 50 over 3. So we want to be careful when we simplify that. When we plug that into the calculator, we want to take 10 divided by parenthesis 50 over 3. If we do that correctly, it will simplify to 3/5. One thing that should stand out to us at this point is that two proportions are exactly the same while one is not matching? That's because that new theorem we talked about is referred to as the side splitter theorem. The proportion can be set up. If we look back to AB, we're looking at AB and BD, the sides that are split, compared to AC and CE. As long as it's the split sides in comparison, they're also always going to be in proportion. While we can't really find our ratio that way, like our scale factor, but it is one way we can set up the proportion. However, it won't work for the bases like of B, C, and DE, because if it's called the side splitter theorem, those sides are not being split at all. So you'll see here, the proportion here is broken up to AB and BD, or AC and CE, but it only involves the split sides, not B, C, and DE. But we're going to see that again in exercise 2. So in the following diagram, we know that RU is parallel to SV, is parallel to TW, which we mark with an arrow. RS is a length of 15, VW is a length of 6, TZ, length of 25, and WZ is a length of 15. We want to find the lengths of ST and UV in this case. So the first thing I'm going to do is solve for ST. We can use the split sides now. So if I start with 25 over X, it's going to equal 15 over 6. I don't have to use the entire side because of the side splitter theorem being a possibility. When I cross multiply, we end up with 15x equal to 150. And when we divide both sides by 15, we get x equal to 10. So that means our length of ST is equal to 10. We're going to do it one more time for Y. And we can use the same 25. We can jump over and just use any part that we want. And I'm going to use the 15 since that's corresponding across here from the Y. So 25 and 15. On the other side, we'll use the 15 and Y. Cross multiply, we end up with 25Y equal to 225. When we divide both sides by 25 in this case, we end up with 9. And that means our length of UV equals 9. So we can use any portion of the side splitter as long as the lines are parallel and we know they've been split in that proportion, it is okay. Basically, what we should also know is that the converse of the side splitter theorem is also true, meaning that if we're setting up proportions, then we can justify that the lines have to be parallel. One thing I want you to look out for right in the beginning, though, is there is a typo, number 3. Change that bottom left fraction to BC. So first, we're going to verify that our side splitter theorem does work. So we're going to take AB, which was 10, over BC, which is 8, equal to AD is 15 over DE is 12. When we cross multiply in this case, I am going to end up with 120 equal to 120. So that does check out so far. So we know that these sides have to be parallel. That's what we're getting out of this. Now, in the second one, we're comparing AC, which is the whole side of 18, over AB, which is 10, equal to AE, which is 27, over AD, which is 15. And when we cross multiply, it is still going to be in effect that 270 is equal to 270. So that is true. Now notice we can find a common ratio in this case because it is comparing a small triangle and a larger triangle. The shapes and the angle measures are all intact here. We're referring to this ABD as well as this here. So we can do the common ratio in either way, but if you look, we have 18 over 10 and 27 over 15 already. If I simplify either one of those, I can divide them both simplify, well, if I simplify either of them, that's just going to end up being 9 over 5. So 18 and 10, if I divide it both by 2, 27 and 15, divide it both by 3, but our common ratio is 9 over 5 here. That being said, give a dilation that would show the triangles are similar. Well, anytime we talk about a dilation, we need a center. So the point that does not move is A. So dilation centered at A with the scale factor, which we call K, and I'm going to say 9 over 5. And if we were getting smaller, if we wrote 5 over 9, that's okay too. And the final piece here, we know that since the triangles are similar, that the angles are congruent, and these types of angles are congruent corresponding angles. They're only formed if the lines are parallel. So, similar triangles have congruent corresponding angles formed by parallel lines. So parallel is a big part of this unit, and especially the side splitter. Side splitter theorem only works if the lines are parallel, and vice versa. If the lines are parallel, then we'll be able to use side splitter. Now, exercise 4 gives us 2 Regents questions. In this moment, I want you to pause the video and try them both on your own. Then we'll come back and talk about it. Be careful to see if you can use the side splitter theorem, and we'll look at. Welcome back. So if you've gone through exercise 4, you can see that we have the 2 different examples completed now. So let's focus on A first. You can use side splitter in A if you choose to. We can set it up as 5 over 2 and x over 5 because it's talking about the split sides. When we cross multiply, we'll get x equal to 12.5, but be careful. Notice that I called x qt when we wanted the full length of qr. So that means with the 12.5, we have to go and add that smaller piece of tr to get 17.5. The Regents is full of questions like this that have tricks that we have to watch out for. So when setting this up, you could have also done it as maybe 7 over 2 and x over 5. That will work now. So you could have done it that way. Over here in B, we cannot use side splitter theorem. Notice it wants AC. AC is not being split. It's one of those sides that does not have a connecting piece. So AC and DE are involved. We're not using side splitter, which means we have to set it up as 4 over x equal to 12 over the whole side of 36. Now your proportion may look slightly different, but as long as you use 36 and set up the corresponding pieces appropriately, you would end up with 12x equal to 144, and that's going to have x equal to 12. So in these cases, both Regents questions both want to be taking their time to make sure we don't make any silly mistakes. The final Regents question that we have on here, in exercise 5, we have triangle ABC, points D and E are on the sides respectively, and we know that we have parallel DE and AC. Now we want to be careful reading this part because it's saying that EB is 3 more than DB. DB is our comparison one. That means DB is x and EB is 3 more than x. So we're going to have x plus 3. AB, the whole length, was given to us as 14. And CB, the whole length, is 21. So setting up that proportion, there's different ways we could do it. One appropriate way would be x over 14 equal to x plus 3 over 21. Now remember, I've talked about how there's different ways we can set up these proportions. So as long as you're distributing becomes the same thing, what you want to look out for, though, is that 14 here is multiplying to both of these pieces. So we should have 14x plus 42. We want to distribute it to both parts. And then we can subtract the 14x from both sides. That means we're looking at 7x equal to 42 and x equals 6.